lead developer of VMD, which is the Molecular Visualization and Analysis program we develop here at the NIH Center. Our VMD page has a large number of different tutorials, so you've been asked to go through one of them, I guess, today in the hands-on session, but there are actually quite a few other topics you may find interesting or valuable for your research, and these are just a sampling of them. And these different tutorials, the one you're going to go through today is sort of the basics of VMD. It doesn't get into a lot of the deep capabilities of the program, but it just gives you sort of an overview of different features it has and the kinds of things you can do with it. Some of the other tutorials get into greater depth, and they cover other topics that are more intricate in terms of the science content. And some of them, in particular, I like the quantum chemistry visualization tutorial by one of my colleagues. Is particularly interesting for people who want to do unconventional visualizations, because he has a lot of examples in that tutorial about how to develop things that are sort of unique to your particular task, and so that's worth looking at too. So VMD is a widely used program. It was originally developed for viewing molecular dynamics simulations, but over the last 20 years it's been evolving to support a broader variety of different types of molecular simulations and structure visualization. And today, aside from very large MD simulations, like the HIV capsid here, I can also visualize things like lattice cell simulations and also experimental imaging data like cryo-electron tomography and single particle cryo-EM. VMD has a very large user community. We have more than 100,000 users. About 16% of those people are NIH-funded researchers here in the U.S. We have a large number of citations. VMD gets cited about once every 3 hours, so that's very exciting. It supports a wide variety of data types and molecular file formats, and most of the public databases for structure data and density maps and so on. And it covers a wide range of structure sizes and timescales, ranging from things like you'd see in a quantum chemistry calculation with tens of atoms, all the way up to large subcellular organelles and structures like these, and then all the way up to lattice cell simulations. And one of the sort of unique features of VMD relative to other tools, both in the past and present, is that it was designed from the very beginning to be user extensible. So, VMD, as you see it when you run it today and as you continue to play around with it, it has a lot of built-in features, and they are sort of covering the wide range of things that a typical scientist might do. But as you know, you get into the details of your particular project, you start needing things that no program offers. And so one of the things that VMD allows is for you to extend the program with your own scripts and your own user interfaces, so you can customize what it does and how it does it for your particular work. And so this is a more advanced aspect of the program, but it's something to keep in mind, particularly for labs that develop their own software tools or their own simulation methodologies. So VMD incorporates tools for preparing simulations and analyzing and visualizing the results of those simulations. And this is, as I say, sort of the bread and butter of the program. In recent years, we've put a lot of effort into extending the program to interpret and process sort of multimodal structural information. So when you have a combination of X-ray crystallographic structures and information from cryo-EM or cryo-electron tomography experiments, you can superimpose those, dock those together with some of the tools that are included with VMD and NAMD, and it, of course, connects with many other tools in the field. So I would say the other area where we've put a lot of effort into VMD that makes it sort of special or unusual is that it takes advantage of advanced hardware technologies like GPU acceleration, SIMD vectorization on the latest cutting-edge CPUs, and we can run VMD on everything from a laptop all the way up to very large supercomputers with thousands of nodes. And so that is also sort of an unusual thing compared to other programs like it. So the goal of a lot of the simulations that people do is to use the computer as sort of a computational microscope, and this gives us access to spatial scales and time scales that are difficult or impossible to reach with purely experimental means. And combining this with experimental information gives us a view into things that we wouldn't be able to study dynamically otherwise. And so these are just examples of the kind of information that you can load into VMD, for example, like the tomogram in its raw form, and its segmented and labeled form, and then in the lattice cell simulation. Those are three representations of the same cell structure shown in VMD in different modalities. The most recent version of VMD was released in November of last year. We have about 20,000 users as of a few weeks ago, so we're getting a lot of people trying it out. Some of the newest features, and I'll highlight these today, and you'll hear about some of them from my colleagues later today and this afternoon. One of the key things that I worked on was new rendering techniques that allow you to produce very high-quality images very quickly using GPU acceleration and the state-of-the-art CPUs. VMD can now load vector field volumetric data. It can load large cryo-ET tomograms with support for a bunch of extended forms of MRC files and things written by tomography tools like IMOD. It supports NanoShaper, which is a tool for calculating molecular surfaces and cavities. One of the other things that VMD now is able to do on large-scale supercomputers is to run in parallel their new scripting commands to allow you to develop your own analysis workflows that can run on thousands of nodes, and this will allow you to run those things much more quickly than you ever could on a conventional laptop or a workstation. You'll hear today about QuickMD, which is a new tool for preparing and analyzing molecular dynamics simulations using a sort of wizard guided protocol that will help guide you to both understand and perform the common simulation tasks. And the new version of VMD has been ported to a bunch of new platforms, and one of the ones you'll get to play with this week is the Amazon EC2 Cloud. So you'll be able to run VMD on the cloud instances that everybody's set up. I don't know that you guys have that all sorted out as of last night, so great. So there was a little stumbling block. They weren't going to allow you to use the GPU accelerated nodes for the workshop accounts that we had all of you guys set up. So hopefully we've got that sorted out now, and you'll be able to access those. Aside from the cloud, VMD now runs on several new types of supercomputers, and those of you who are interested in running VMD on the large-scale HPC machines, I'm happy to answer any questions you might have about those. If you're running it here in the U.S. on the Texas Advanced Supercomputer Center or Blue Waters or one of the Department of Energy supercomputers, feel free to ask me questions about that, and I can tell you more about that. So I think Joelle will be telling you a little bit about QuickMD in the next lecture, so I'm going to go past this, but this is just an overview of what QuickMD is able to do. And one of the things that I think is very important about our efforts in developing QuickMD and tools like it is to improve the reproducibility of the structure preparation steps and model simulation workflows that people perform, and that's one of the things that QuickMD will help you with. VMD has a tool for helping you parameterize novel compounds, so if you're doing simulations of drug compounds or other things that are not part of the charm force field, VMD includes this tool, Force Field Toolkit, that will help guide you to run the necessary quantum chemistry calculations and do the necessary work to come up with the parameters or evaluate parameters to determine if they are good enough for your intended purpose. Right now, this tool uses Gaussian to do the quantum chemistry calculations, but the plans in the coming future are to broaden it to support other free academic codes like Orca and others. So anyway, this is more of an advanced tool, but if you're interested in doing those kinds of simulations that require parameterization, you should be aware of that. As I was telling you earlier this morning, one of the key capabilities of VMD that makes it different from other programs historically is its ability to be extended by the users themselves, so you don't have to be a computer scientist to extend the program to do new things. You can do it using high-level scripting languages like TCL and Python, and you can do this by writing scripts that either work in a command line fashion, sort of what we would call a text mode interface, or you can use those same scripts to develop graphical interfaces for things. And in fact, if you look at the source code of VMD as it is distributed today, there is roughly twice as much code in the form of scripts now than there is in the form of C++ or CUDA or the other more expert-oriented languages. And so this allows VMD to be extended by anybody, and you can even take the VMD that's running on your laptop and add new things to it right now without having to compile anything. You can just write new procedures and scripts, and you'll learn a little bit about that in the VMD tutorial if you work all the way through it. And so that'll be a good introduction to the ideas behind it, but of course you can go much further. Another thing that you can do with VMD, if you are familiar with lower level programming and languages like C or C++, if you or your group develop your own simulation tools or you work with data that VMD doesn't at present understand, you can develop new plugins that are able to read and write new molecular file formats. And so quite a number of these plugins have been written by VMD users over the years. I think we have about 75 different plugins presently, and I would guess something like 20 or 30 of those were contributed by outsiders. In the case of the other plugins, the GUI plugins or text-based analysis plugins, if you look at just a subset of the plugins that exist, all the ones that are shown here in green were developed by people outside of our laboratory on their own for their own purposes. Just a couple of interesting examples would be the free energy analysis plugin developed by Chris Chipo and his colleagues. And I think you'll be hearing more about free energy later this week, and I'm sure he will demonstrate how that works at some point as he discusses that. Some other examples are Bendix, which does helix analysis and draws some very nice figures. They're easier to understand and produce better looking figures of these helices. And Normal Mode Wizard, which works in concert with the ProDie tool that some of you may already be familiar with. So I'm going to switch gears a little bit and tell you about the visualization aspects of VMD, and that's really where I put most of my effort recently. And just to give you an overview of what VMD is able to do, why it's designed the way it is, and sort of what its strengths are, and the concepts behind how it works. So just to give you an introduction, if you think of molecular visualization relative to other scientific visualization pursuits, some of the things that make molecular visualization challenging are the fact that we have very large, geometrically complex scenes. Today, this would be considered a relatively small structure. This is a million-atom satellite tobacco mosaic virus, and it's drawn showing the capsid and the ions and the RNA in the interior, and a little slicing plane that's colored by electrostatic potential. And in an image like this, there are lots and lots of things to see, and making a clear image out of a structure like this is quite a challenge. And so some of the things that a visualization tool needs to do for molecular scientists are to show spatial relationships very clearly. So you want to see what things are in front, what things are behind. These 3D structures are very complicated. One of the things that can help, of course, is to move the structure around, so interactivity is very helpful. Just, I don't know if you know this, but owls, if you ever watch an owl will move its head back and forth as it looks at something. And the reason it does that is because it'll give the owl a better 3D perception than if it just sits still. And that's true for us as well. So one of the key things you can do when you're looking at a structure is to rotate it around a little bit, just, back and forth a little bit, and you'll get a much better perception. But when you're making a figure for a publication, you can't do some of those things. You have a static image, it doesn't move, and so now you have a challenge. How do I illustrate those same properties effectively? And some of the ways we can do that are to use fog or so-called depth queuing, so that things in the front are either lighter or darker than the things in the back. We can use shadows and ambient occlusion. Who here has ever heard of ambient occlusion? Raise your hand. That's what I thought. So about 2 people out of 30. So there are advanced rendering techniques. Ambient occlusion lighting is a particularly fancy way of doing shadows that gives you a very natural looking image. And the point of this is not, you don't need to become a computer graphics expert. The point of this is for you to exploit your natural visual intuition to just look at an image like this and see the pockets, cavities, and crevices without having to do a bunch of work to create an image that is informative. And so we want to be able to make these scenes that have a bunch of spatial properties and structural properties, and we have, in many cases, time-varying data. So we have a lot of different problems to solve. So to display these structures, VMD can, of course, do the typical things, drawing atoms as van der Waals, spheres, bonds, ball-stick models. We can show quantum chemistry data like molecular orbitals. We can draw molecular surfaces, and we can use some of those techniques to illustrate things like the solvent box in a periodic simulation. We can draw groups of atoms as beads, and then we have higher level representations like ribbons or secondary structure representations and cartoon representations that sort of hide a lot of the minutia of that atomic structure and replace it with a schematic representation that is still informative, or it might be more informative than if you just look at the actual atomic structure itself. One of the things that any molecular visualization tool has to do then, when you're working with these dense atomic structures, is to be able to select and filter what is displayed. You don't want to show all of the structure all the time. The first thing you usually want to do is hide things that you're not interested in. For example, you don't want to show the bulk water in a simulation. You want to strip most of that away. But there might be tricky things, like in this case, we have an aquaporin channel, and the key activity of this structure is to filter water. Aquaporin channels are, for example, in your liver, and your body filters something like a bathtub full of water every day through your liver. And it does it by passing those waters through these very selected channels. If you want to make an informative image of how that channel works, you want to show waters, but you only want to show the waters that are passing through the center of that channel that are doing something interesting. And so that's where VMD has a particularly sophisticated feature, which is an atom selection language. Many of the molecular visualization tools you may have seen in the past, or up to this point, would have used visual selection techniques. Like you might click on something and then it would change its representation, show it or hide it, things like this. VMD has a little bit of a different approach. VMD has always used a text-based atom selection, which, for those of you who are big users of Google, which I assume is everybody in this room, you have a selection language that is composed of a bunch of criteria, and they can be combined. You can use unions, intersections, differences, things like this. You can use spatial selections, so water within 10 angstroms of protein, and you can use things like Cartesian coordinates as part of your selection. So I can say and z is greater than 0. In a selection like this, it gets much more complicated. I need to use a spatial selection for the region of the channel that we're interested in. We don't want to show the whole thing. We can actually use a more complicated equation that narrows down a region like a cylindrical region that's surrounding this channel, and then we can exclude all the other atoms. And if we get even more sophisticated, we can scan through all of the trajectory time steps in a simulation, find just the atoms we want to display, and exclude all the others. So then we end up with a set of waters, only the waters that actually passed all the way through the channel. We can do things like that too. And so you can imagine this can then become very powerful. And a unique attribute of this idea of using a text-based selection language, we can use the same selections both for producing the visualization that you see on the screen and also for the analysis scripts that you write in Tcl or Python. And that's very powerful because it means that as you're developing a script and you say, I want to calculate something, you can use that same selection to check, am I picking the correct atoms for the calculation I want to do, yes or no? You can actually see that you've got the right one selected. And so this gives you a sort of synergistic feature between the visualization and analytical and structure building attributes of the program. And this is particularly useful when you're dealing with time-varying structures, structures that are so large it would take you the rest of a week to go picking things by hand with a mouse. You'd commit suicide long before you finish clicking on all those atoms. And then, of course, we can compute lots of properties. Your atomic structure has various information that's sort of included in it. By default, you have at least the atom names and the Cartesian coordinates. From that, VMD can, if you don't have topological information, bonds, VMD can guess those using various heuristics. So it can complete some structures. It has tools. If you get a crystal structure from the PDB and it doesn't have the hydrogens, VMD has tools built in that will automatically complete the missing parts of the structure and give you the full structure. It has tools for calculating hydrogen bonds, salt bridges, computing various forces and energies if you have the different coefficients you want to use. It can calculate time-averaged electrostatic fields, volumetric maps of spatial occupancy over time, cross-correlations of atomic structures or simulated structures with cryo-EM density maps, and then things like normal modes, principal component analysis, and so on. And so, these are things that we can do after you load the structures into VMD. Just as an example, then once you compute those properties, you can use those properties to further color the structure or select things by those properties. For example, I can use per residue solvent accessible surface area to color the different residues in ubiquitin. I could use the electrostatic potential map that I get from a coarse grain PME calculation to color a little volumetric slice in the space around the molecule. This is an example of something that's done externally. So I think this one was done probably with ProDye or one of the others. And then they've basically loaded a bunch of PCA vectors and shown that as a porcupine plot, so you can see where the principal moments of motion are in this structure. And so this is something that was done completely with a script that isn't built into the program at all. Somebody else wrote a little script that reads input from another program and then draws these little arrows. So those arrows aren't really part of VMD itself. They were part of this person's script. And so that's just an example of the sort of thing you could do for yourself. And then I would say by far the biggest difference between VMD and other programs is when you get into time-varying data. So this is really what differentiated VMD from all of the other programs from the beginning, is that for VMD, time-varying structures are a fundamental concept. It has always had the ability to load molecular dynamics simulation trajectories, and you can have time-varying atom selections, so atom selections that are evaluated every single time step. So if you make a spatial selection that is not necessarily true for all time steps, it'll give you a different part of the structure shown as the simulation progresses. Different atoms will be selected. This is something rather unique to VMD. And then we can have VMD with a little scripting. You can have VMD compute secondary structure on every single time step. If you're used to tools like Chimera and PyMol or others, a lot of them will read the secondary structure records out of a PDB, but they won't compute the secondary structure on the fly. And so this is something VMD does using a tool called Stride. You can see that as the structure is changing, different parts of the secondary structure are changing from one assignment to the other and so on. This is something sort of unique about VMD itself. VMD can also show the results of hybrid fitting methods. I think you'll hear about MDFF sometime this week. Is that right, Joel?
Yes.
Okay, so you got a little intro about it already. So this is another nice thing that VMD can do. You can actually load your MDFF simulation trajectory and watch your fitting progress. And this is another example of such a thing. This is a hexameric subunit of HIV, of the HIV capsid. And you can see that as it's undergoing simulation, the atomic structure is being docked into the experimental density map. So this is just another one of these kinds of examples. And then I'll get into now more of the rendering things. So, if you have so this is where I'm going to depart a little bit from the basics and get more into the advanced features of VMD. But do you have any questions up to this point? So I want this to be interactive. So if any of you have any questions about anything I've discussed prior to right now, this is a good moment to pause or have you ask those questions. And of course, I can answer them later also. Any questions? Yes?
When you do coarse-grained simulations and you try to see the VMD, so is there any way you can have the cartoon structure for coarse-grained or not?
So this is a tricky one. So the cartoon structure depends on having a secondary structure assignment. And the tool that VMD uses, Stride, is designed to work with atomic structures. So it actually wouldn't understand a coarse-grained bead. But what's interesting about that, in principle, you might be able to do such a calculation, but the way that secondary structure assignment is done or prediction is done, they basically evaluate a hydrogen bonding network by distance-based searches and things and evaluating bond energies. And from the result of that hydrogen bonding network and so on, they compute what they believe the assigned structure to be. So the trick is, can you do that for your coarse-grained structure? If your coarse-grained structure has enough information to do that kind of calculation, it's conceivable a person could adapt one of the existing tools like DSSP or Stride or another to be able to do that secondary structure calculation. But if your model is so coarse that you can't do that type of calculation effectively, then probably it would be a meaningless calculation. Yeah. Any other questions? Yes?
What about the bridging? What is doing this?
So there are scripts out there. I've seen others write that will do those kinds of calculations also. But I don't think we have any posted, so that's something you'll have to search the mailing list for. We have a very active mailing list. I don't know how many postings we have on it now, but I think it's on the order of 20,000 postings. And it's searchable both in Google, and there's a little search box on there. And, by and large, any topic you can think of, somebody has asked about at least once before. They may not have an answer that you like, but they may have asked about it before, and it's probably been discussed once or twice. So anything that you're looking for that isn't common knowledge, it's not in the manual, it's not an existing script or tool in VMD before, and this is another thing, even though the program is very extensible, it's worth your time to quickly look and see if somebody has developed a tool before, even though you may not see it on our website, because there are, in fact, groups all over the world that have developed their own VMD plugins, and while they're not located on our website, they do exist in there. It's worth knowing about those, and searching the mailing list is a good way to find out about those things. Others? Yes?
So when adding protons to different proton side chains, does the plugin take into account whether there are other charged residues close by to the side where to add a proton?
That I don't know the answer. Do you know the answer for that, Joe?
To do what? Sorry.
To add protons to different side chains. So does the script consider whether there is another side chain close by and then maybe proton is needed or not?
No, for that you actually have to do the calculation, and then if you are thinking about preparing structure for simulation, you actually have to assign the correct protonation state by, in this case, sharp. That is basically what you are doing, and quick and you assign a patch to that residue, and you assign the correct protonation state.
So you do it by deciding yourself.
You can decide by yourself if you have the expertise, or you can use other tools to evaluate the pKa of your structure and then assign the protonation state of that residue. But as far as I know, there is no automatic way to do that.
Yeah, I don't. That was my default assumption anyway. Is I don't think that the script that exists is that sophisticated, but yeah, I don't. Off the top of my head, I'm not aware of a tool that does precisely what you're asking. But, again, check the mailing list. You never know. Somebody might have a better answer than I do. You have to remember also, my background is computer science, not computational biology, so I've had to learn a lot of these things over the years. And I'm not a modeler in the same way that all of you are. So you probably have various questions that I will have to defer to Joel because he's more practitioner than I will have. So, other questions? All right, well, then we'll continue. So one of the unique areas in VMD going back some years is VMD supports a rendering technique known as ray tracing. So just so you know the technological sort of names of things, the typical rendering that you see in a tool like VMD Chimera or PyMol is known as rasterization, and that's using a computer graphics programming API known as OpenGL. And so rasterization is able to draw things very rapidly. This is what video games use. And rasterization can draw, in particular, things composed of zillions of triangles very quickly. but historically at limited fidelity. And this is, in part, they make a lot of trade-offs in the algorithm to be able to draw things rapidly, but at the expense of visual quality and lighting fidelity and things like this. And it turns out that for the kinds of structures we want to render, both due to the fact that we don't draw things that are triangular, we draw a lot of things that are composed of spheres and cylinders and various extrusions like the ribbons and so on. And we want to draw these smooth curved surfaces, and this is actually very difficult to do in OpenGL. And so as you start working with modeling larger and larger proteins or protein complexes or larger subcellular units, you will find that OpenGL starts to get very slow. Even a program like VMD, you get 100,000 atoms and draw them all as spheres, that ends up really taxing your GPU. And so one of the things that's an alternative to rasterization is ray tracing. Ray tracing is a different way of producing images. And the advantage of ray tracing, or one of the advantages of ray tracing, is that it is easier to incorporate much higher fidelity lighting and shading, and you can do things that are closer to physically accurate. And in fact, the highest end ray tracing techniques are what Hollywood uses, and they are sort of physically correct rendering where all the light that bounces around in a room is fully accounted for. And this sounds at first like overkill when you conceive of how you would use this in molecular visualization, but the point of it, we're not doing things at a Hollywood level. We don't care about it being physically accurate lighting because in reality these atoms are smaller than a wavelength of light anyway. But what we want out of it is we want to exploit the intuition of the viewer to understand the complex structure that you're looking at in 3D, and we can exploit that lighting the same way if you looked at a scene like this room, you would immediately understand all the spatial relationships. You'd feel like you're there if it's properly shaded. The same is true of the molecule. The scale is wildly off, but that's the value of it for us. And so over the last 15, 16 years, we've basically adapted VMD to be able to support ray tracing, originally in sort of a batch mode. Back in the mid-2000s, it might take somebody 25 minutes to render one image for publication, for their paper, their journal article. And one of the things we've been doing more recently is making that much faster, and I'll tell you a little bit about that. So the first thing that's beneficial about ray tracing is, as you use VMD and you work through the tutorial, you'll see that these graphical representations have a parameter called resolution. And that's the reason they have that parameter is because for this interactive rasterization for OpenGL, the video games, we have to draw things with lots of triangles. And so there's a trade-off between performance and visual quality. The more triangles we draw, the smoother things look, the nicer the images. But that means it runs slower. So if you're trying to play a trajectory, you might use a very low resolution, and then it'll play faster, or it'll rotate faster. But then your spheres and your atomic representations look more like a stop sign and less like a sphere. So that's not a desirable outcome. One of the things that's great about ray tracing is that we don't draw things composed of zillions of triangles. They are drawn as their perfect geometric primitives, and they're solved mathematically down to a precision of a pixel. And so that means you don't have to worry about things like these resolution parameters. So when you go to making figures for publication, rather than doing a snapshot in OpenGL, what I'm going to advise you to do is learn how to use the ray tracing features in VMD, or in fact, the same would be true of the other tools like Biomolecules and Chimera. I think both of those two tools have similar things now also. And so the value of that is then you will get round spheres. They'll always look round. You're not going to have little weird visual discrepancies. The images will be much more pleasing. And the other thing that you get out of it is much higher quality lighting. Like this kind of rendering here where you see all the water atoms or water molecules here, you can see that they look round. You see some depth to them, and then you can see some gradation where there are little pockets and cavities. These are things that are trivial to see in this ray traced image, but to do that with OpenGL would be nightmarishly difficult. And one of the things you're trading off then is ray tracing requires more computation than rasterization OpenGL does. But you get these nice quality, high quality images, and the best part is you don't have to spend as much of your time fiddling around with parameters. It will look good mostly by default if you use a lot of the defaults we have set. And I'll show you a little bit about how that works. The other thing that's cool about ray tracing, and this is just starting to become a factor, is that ray tracing, there's a computational scaling issue. With rasterization, the factor that impacts performance is how many things you draw, how many objects. And so that's how many triangles, how many spheres, how many cylinders. With ray tracing, the number of objects isn't really a problem unless you run the machine out of memory. And in fact, the factor that controls the performance of ray tracing is how many pixels, so how big the image is. So if you're to race a ray tracer versus a rasterizer, the ray tracer will win for the billion atom cell, so long as you don't run out of memory. But the rasterizer will win for the billion pixel poster. So there's the two extremes, right? And but the ray tracer will always win on quality. So this is why we want to use a ray tracer rather than OpenGL. These are the same virus capsid cut open. So this is that satellite tobacco mosaic virus. This one is drawn using OpenGL with the typical lighting and shading approach. And this one is using interactive ray tracer and VMD with ambient occlusion lighting. And that's giving us an immediate impression of the different pockets and cavities and the depth of the depression in the core where there's empty space where the RNA goes. So just looking at these two images, OpenGL, ray tracing. So this is why you want to use ray tracing in VMD and to whatever extent that it exists in the other tools. And so that lets us do things like render a picture like this much more clearly. You can very easily see the different pockets on the surface of this virus. This image is kind of interesting because it combines, in the last one I did this on purpose, right? I used no extra coloring or anything. So this is basically if you put zero effort into it, this is what you'll get out of OpenGL, and this is what you get out of ray tracing. So the value is you didn't have to do anything to get this. You just turn it on and say go. But if you then go further with it, you can make images more like this. This one is combining a radial coloring on the capsid to accentuate the extremities of the surface and their protrusions in space, and in addition to the shadows that the ray tracing is giving it, right? So both of those things are now working together, and so you're emphasizing that information more by applying both the coloring and the shadowing algorithm at the same time. And this one, there's also depth cueing, so you can see the atoms in the front are very saturated. They have a strong color. And as you go back in the scene farther away from the camera, they're sort of washed out. And that's what fog does. And so by using fog in combination with the lighting, you can also accentuate depth more even than it would just with the lighting itself. So you can use these different things together to make more compelling renderings. Here's another example. So this is, I picked a EFTU, which was a molecule of the month back in about 2007, and I just rendered the same structure with a bunch of different material properties. So one of the material properties that's built into VMD is a little outline shader, puts a darkened edge on anything that you draw. And so you can use that darkened edge to sort of accentuate the stacking of various structures. This is kind of interesting because it gives you a 3D impression that's a little more, it pops a little more even when you're using OpenGL for your rendering. This is another one that sort of mimics in a very inexpensive way the rendering style that David Goodsell likes to use. So if you look at the PDB molecule of the month, he often renders these very nice, they sort of emulate like a pen and ink kind of drawing with a pastel shading of the interior. And again, this is using the outline shader in VMD combined with some very diffuse lighting. And so this is, you might say, well, what would I do with this? Why would I do this? Well, one reason would be if you want to show something in the foreground that's a detail, but you want to keep a larger part of your complex or your structure in the background merely as context. You don't want to take it away, but you want to de-emphasize it. Shading method like this can be used to de-emphasize something while keeping it in the scene. So that's a useful use of that kind of scheme. Then you, of course, have your sort of typical glossy shaders, and then your ambient occlusion lighting with it, sort of a chalky material. So this looks like more like something to be made out of rubber, like a pencil eraser or a piece of chalk. And so, if you look at the different things, this one is showing, you can see the interior is darkened because the light is blocked, and that's something you don't see in the others. And this one, it looks more flat. You de-emphasize the 3D structure. It's just sort of there. It takes up space. And then the others have their own appearance. Here are some other examples. This is another one. This one is an interesting example. I like this one because it's on a gray background. You often are forced to choose your background color for various reasons that aren't under your control, either because it's a figure that you want to be on the cover of a journal and the journal likes white backgrounds, or it's for your PowerPoint slides and you have a particular preferred background, or you want it to be blue to imply that there's solvent there, or who knows what you're after. This one's a nice choice because gray is sort of an intermediate color. Regardless what foreground colors you choose, things that are either very bright or very dark, gray is sort of in between, and so it doesn't distract you from the foreground objects. If you chose a black background, then the bright colors would really stand out, and the dark area here would not pop as much as it does here. Here you have a nice contrast, and it highlights, like if this had a black background, you wouldn't see this part nearly as well, right? So this is another thing. Yes, sir?
So these examples you're showing us, are these RT or OpenGL?
These are all rendered with the ray tracer here. All the ones that I've been showing you thus far here, since I began the ray tracing, all of these are ray traced images up to here. So I will say that there are ways of getting crude approximations to this in OpenGL, but it comes at a very high performance cost, and there are quality trade-offs, particularly when you get into rendering movies. That's where, there are ways of faking ambient occlusion lighting or approximating it in OpenGL, and they use these for video games. And in a video game, you don't really care. But when you guys start making movies that you want to present in a scientific lecture or something like that, some of those trade-offs are not very good for what we do, because you see strange fluttering and things like this in the corners of the image, and that for a scientific presentation, that would be too distracting. In a video game where you're just trying to kill the opponent, it really doesn't matter, right? So you forgive a lot of things for a video game. So that's the thing, is the ray tracing, we don't take any shortcuts. We do it the hard way, and we get results that are more predictable. So that's a little silicon nanocore. And this one, this is again one of these cases without the ambient occlusion lighting. I saw what this looked like in OpenGL. One of my colleagues rendered this, and I said, wow, that looks really flat. What is that? And he said, well, it's a nanocore. And I said, it looks two-dimensional. And I said, why don't you render that with the ray tracer? And he was blown away, because when you just have the right lighting, you can immediately see that this pore has depth behind that structure. And without that shadowing, that makes all the difference on the understanding of the spatial relationships there. And so these are, sort of easy examples I'm showing you, but that's the point of these techniques. Some of the other things that ray tracing does particularly well are transparent objects. When you have a bunch of transparent shells, like let's say you draw a bunch of concentric transparent surfaces, like these are photosynthetic light harvesting structures. You can see little green circular areas are chlorophylls. These are little antenna complexes. The green ones are LH2s. And you can, these can be like right here, we have several of these overlapping, and we're looking through a bunch of transparent geometry. Doing that correctly in OpenGL is very difficult for reasons I won't get into. So what that means is most programs cheat. To make it fast, they cheat, and therefore it doesn't look quite right. And you probably have seen various artifacts, both in VMD and in other programs, that are the result of the cheating that we do. And one of the values of ray tracing here is there's no cheating. It looks right, and no matter, and when you're rendering a movie, again, this is a bigger deal for rendering movies than it is even for a still image. With a still image, you can fiddle it around until you're satisfied with the image and you say, good, I'm done. But But when you're rendering a movie and it's got 18,000 frames in it, you don't want to have to worry about, do I have to fix something in the middle of the movie that doesn't look so good? So that's another value of using a ray tracer. This is another one of these examples where if you cut open this structure, in OpenGL it looks very flat and two-dimensional, and here you can see much more clearly the parts that are in the foreground and the parts that are behind. Again, so I'm sort of beating you to death on the shading stuff, but I feel it's worthwhile. And this is a more extreme example of that light harvesting structure. This is about a 10 million atom chromatophore structure, and it's drawn with largely transparent surfaces. Another cool thing that VMD has is a transparent material property that lets you, so it's transparent rendering, but we have modulated how transparent it is, so the edges look less transparent, which gives you some context about the boundary of the structure. But the flat, like a flat face, normal to the viewer, is completely transparent, like it's not there. And that's why you're able to look right into there, and you see the boundaries of those little LH2 rings, but you can look inside very easily. It doesn't obscure the interior structure as much. And so if I go back to the previous one, that's the same shader that's being used here. And that's what, so that's why when you look here, it's like there's nothing in the way at all, but you do see the boundary just around the edge. Yes?
So do you think, for example, for the large image that you showed afterwards, do you think that would be possible to do with a regular computer, or you need?
Oh yeah, this is definitely possible to do with a regular computer. I did do it with a regular computer, just a PC.
Okay.
This doesn't require a supercomputer. So this structure here with no solvent is about 10 million atoms. VMD takes about 12 bytes per atom for memory. So, you're talking about, what is that? That's 1.2 gigabytes of memory. That sounds like a lot back about, when we were first building this, that was a lot of memory. Now it's not a big deal anymore. I think even your conventional laptop can make an image of this. It's that, like a Windows PC might be challenged, but not so much, like a Linux machine would have not even a challenge.
Okay.
So a couple of gigabytes will take care of this, no problem. Other questions? I thought I saw a hand. Everybody's good?
Can I just
Yeah.
I will say that for you guys to make these pre-renders and all these beautiful pictures that we do in VMD, we advise, or at least I advise, Linux machines, Linux platforms, because you have access to all these features, while in Mac and Windows, the VMD itself is limited to what you can do with the renders.
And it takes a long time to develop the low-level technology that goes into this. And so I haven't gotten to it yet, but I'm going to show you in the next few slides some of the advanced rendering features that are presently implemented only in Linux. Now, the plan, of course, is that we get those implemented on all the platforms, but we have to overcome various barriers to doing that that are uninteresting to you. And so anyway, but this could be rendered, for example, on a PC. This should not be a problem. And in fact, I can probably give you guys a little demo of rendering that interactively. So these are other virus structures. Again, using the ambient occlusion lighting a little bit. This one has sort of a soft ambient occlusion lighting. The shadows aren't very dark. And then I think you colored it by electrostatics or by the residue type. I've forgotten. I think that's rabbit hemorrhagic disease virus, and this one is poliovirus. Poliovirus is a great example because you have the structure cut open. And this is, again, one of these cases where having the shadowing makes it clear that these things are on the interior of this capsid surface and that this is in the interior below that. If you drew this without the ambient occlusion lighting, this looks very flat, and you don't get this impression of this triangular cut and how far inside the RNA is. Just looking at that, it's much more obvious. Another thing that we can do with a ray tracer that is difficult to do with OpenGL is what we call depth of field. If you've ever seen fancy photographic images or portraits, photographers will use depth of field so that the subject that's in the foreground, or the thing that they're trying to focus on, is in crisp focus, like this area, or the things in the front, and then the things in the background are blurred out, and that's called depth of field. And the blurred out images, or this part, is what we would call bokeh. And so we can use that to, again, kind of like that other, the material property I showed, the good cell shader that sort of de-emphasizes the detail. You can use depth of field to do that for your molecular structure also. And not only, right here we've shown in a simple example where the depth of field is focused on the front of the molecular structure, but we could also focus at any point in the structure. So you could look at, with your camera, look at a particular part of the structure and have that area be in crisp focus and the other parts be fuzzed out. And so then you can do other things where, like this one, we really didn't use any shadowing at all. This is basically using no shadowing and a conventional transparent surface that's extremely transparent, and you can just barely see that it's there, and it doesn't obscure the interior at all. And sort of that's another. So this is more like what you would do with OpenGL. And in fact, with the high-quality OpenGL GPU, you can generate this kind of image in VMD interactively. So it isn't that it's impossible, but it's just challenging. You have to put some work into it to get a good figure the old-fashioned way. One of the other things that ray tracing is uniquely suited for, which is a new, very, very, very new feature, is omnidirectional stereoscopic projection. So how many of you have heard of an Oculus Rift? Oh, you guys, really? How about VR headsets? How many of you have heard of those? Yeah? So about half. Okay, well, so a big area of ongoing activity right now in the marketplace is they're now selling 3D headsets to video game players. And what these headsets allow you to do is they give you a stereoscopic projection of the world around you. You can turn your head all the way around. You can look up. You can look down. And you feel like you're actually there. And the use of stereoscopic perception, so if you've ever gone to a 3D movie, it's like that except for it's interactive. So it isn't just watching something that's been pre-recorded naturally. You can actually turn your head and look around and see lots of things. So one of the things we can do in these ray tracers now is we can, and I'm going to switch out to YouTube, we can render omnidirectional movies that are in stereo, and then you can look all around. So this is actually YouTube. You've probably never seen a YouTube movie like this. I can actually look all the way around. I'm inside an aquaporn channel movie. I'm going to go back to the beginning here. Hopefully my network connection still works. Maybe not. But so right now we're just in one frame of the movie. I think my laptop's having a hard time, but I'll show it to you later. But basically, even for a still frame in that movie, you can see I can use my mouse and look all the way around. And that's pretty cool, because that gives you the ability to show somebody three-dimensional rendering of your molecular structure. And in fact, if YouTube would cooperate here, we'd be able to show you a moving structure. And you can wear a little 3D headset and look around, and as you look around, the scene adjusts. And this will work on your smartphone. So how many of you have smartphones here today? Right. So that's something you know about. Your smartphone can play this. And this little icon that's in the top left corner, this is what is an indicator that you've got a 3D movie in YouTube. And so buying like a $20 pair of VR goggles, you can put your phone in the goggles. You could take it with you to your next poster session. And then you can render a movie of your simulation. And at your poster session, when people want to see your structure, of course they can look at your poster, but I would say that having them look around in 3D at your atomic structure is much more appealing. And it's sort of nice because, it's not like having to give a live demo on the computer. It's a movie, it's pre-recorded, you've already got it arranged, but it still has that interactive feel, and so they can kind of look at the parts that they're interested in. So that's sort of an area of ongoing activity. So I'll show you that more later when I have maybe down in the coffee break. We'll let you guys play with that. And somehow we got lost off our slide here. Let me get back. So we were here. And another thing that's kind of cool is, aside from those, we can also do things like render movies for display in planetariums. So this is an interesting new area. A lot of astronomical planetariums formerly had hardware star projectors, and nowadays they use digital projectors just like everything else. And that means for the first time ever, they can show things in a planetarium that aren't stars. And they are very eager to have other science content to show in these planetariums because the viewing public is, they've seen a lot of stars, but they'd like to see other things too. So this is a simple example rendered in VMD. And so you can do this with the version of VMD that was just released back in November. So what's the gotcha? So the gotcha about ray tracing is the rendering technique. It gives us all these high fidelity rendering output, but there's a lot of floating point arithmetic. It requires a lot of number crunching, and so to make this fast, and particularly to make it interactive, because you've probably seen, there are tools out there like Pavre. How many people have ever heard of Pavre? A few people. So Pavre is a ray tracer that's been around for 20 years. I wrote another one called Tachyon. Those have been around for a very long time. But one of the big deficiencies when you start thinking about, well, what do you guys need to make a good scientific image for a publication is you want it to be interactive, because when you have to take a minute to render an image in a batch mode sort of way, that's a big impediment for you, because there might be 50 different things that you want to adjust or change or fiddle with. And the problem is if it takes a minute to get an image, then you have to sort of blindly go back and adjust a bunch of things, and this is not convenient. And so now in the latest versions of VMD, we have an interactive ray tracer, and there are two versions. One uses GPU acceleration, and the other one uses Intel CPUs. And I made a little simple movie recording of what it looks like to use this interactive ray tracer on that million-atom satellite tobacco mosaic virus. So to make it interactive, we have a progressive refinement approach. So the renderer makes a scene very rapidly, and while you're rotating it, it's sort of in lower fidelity, and then as soon as you release the mouse, it refines the image to a higher quality image. And so you can see these little speckles on the bokeh of the out-of-focus atoms that begin very speckled, and then after I release the mouse, you see the lighting flashes a little bit, and then they start to refine, and they get fuzzy, and they become a smooth image like what you want in a final rendering. And so you can very easily interactively adjust the scene however you want, and change the perspective, move the camera in and out of the scene, all that kind of stuff. And so then I'll work on now just a little bit about the analytical features of VMD. So, of course, a key part of VMD is its ability to load simulation trajectories. And we have a tool in VMD called Timeline that will load, you can load a trajectory in VMD, and it can do various calculations on that trajectory over time and plot those in a 2D heat map. And so this is an example where we have the horizontal axis is time, and the vertical axis is structure, and then the colors are showing you the change in secondary structure starting at the beginning of the simulation and going to the end. And so you can see as it stabilizes, this is a folding simulation. We have tools for taking a trajectory and computing volumetric properties like the occupancy of magnesium ions throughout a simulation. And so here we've watched those ions jiggling around in the simulation, and as they spend time in one spot, it kind of adds up that time in each little grid point in space. And after the fact, we can then draw probability density isosurfaces around those regions, and we can give them different colors. And so when you have very high probability density, you get the dark blue. When you have slightly less, you have this light green, and we've drawn those surfaces in a transparent way. And then the least probability density would be the red there. And so that's another such example. One of the things that VMD can do on large machines, adapting the program to run on supercomputers, not only can you run VMD on your desktop or your laptop, but you can run it in parallel on large machines, and that means that you can do things like render movies in parallel. So if we take a large HIV structure and we render it with OpenGL, some of the rendering time is associated with drawing some of the other parts or related to things like updating atom selections or deciding what parts of the structure to recompute for things that are varying with time. And we can use a larger number of compute nodes to render those things faster. And of course, there are other parts which are just strictly disk I/O, reading trajectory frames or writing images to disk. So for example, if we run this on Amazon EC2, with one node, it might take 600 seconds or about 10 minutes to render this movie, of which about 10% of that is spent on I/O. Or if we run on 32 nodes, that we've crushed the rendering time, and so most of the time is then spent on disk I/O. And we've taken the runtime and reduced it by a factor of 7 or whatever. So you can see the impact of that as we speed it up further. And so that, if you get to rendering long movies, like some of the ones we've done here that have tens or 20s of thousands of frames, this can be very helpful, particularly if you're using high-quality rendering and things like that. And we can do this using off-screen rendering. So this is an image that was done using just OpenGL, using a special interface called EGL. You will have seen after you run through the tutorial today, you'll know how to use VMD interactively, but VMD can be run in a batch mode, and you can render images from scripts without interacting with the program at all. So if you have things you want to calculate in parallel, or you have an analysis where you want to produce images as some work is being done in a simulation or otherwise, VMD can produce the same images in an off-screen buffer without a GUI and without any window or any of that, using features like EGL as it can using the conventional version. And we have an EGL version of VMD available for Linux on the website now that you can use. And it does all the normal stuff. You can draw text labels and things like this and color things like by electrostatic potential and so on. And so this is an example where I'm going to show you now where we use the parallel computer to speed up some of the more computationally demanding analyses. So when we're doing one of these hybrid MDFF hybrid fitting simulations, one of the things we want to do is measure the quality of the fit between the all-atom atomic structure and the experimental density map. And the way we do that is we compute a simulated density map from the atomic structure, and then we calculate the Pearson correlation, or what we call a cross correlation, between the two, the simulated density map and the experimental density map, and then we get a number between 0 and 1. And so if we color code the structure by a spatially localized cross correlation, we can see regions of the structure that have a good quality of fit in blue or a poor quality fit in red. And so this is a way of identifying this both visually and quantitatively, and we can use this in concert with both the visualization tools in VMD and also with this timeline tool, so we can see the quality of fit of different parts of the structure. This is the structure vertically at different residues, and this is the simulated time in the MDFF simulation. We can see the red regions basically starting to go green and then finally to blue towards the end. And that at the end, we've got a good quality of fit with just one little troublesome little area right there that's left for somebody to pour over and fix. This is all fine and good for a very small structure like this, but what if we have a big virus? And what if we want to calculate the quality of fit separately for all the different subunits in the virus? Now we have a serious calculation. So this is a 700,000 atom virus and a rabbit hemorrhagic disease virus. We have a trajectory with about 10,000 frames. There are 720 of these structural components. And if we want to calculate the cross-correlation for every one of those separately over the entire trajectory, this starts to become a significant calculation. If we did this with the conventional algorithm that most programs use, and I've tried various of them and we've benchmarked ours versus theirs. If you do this sort of the normal way, this would take about 5 years using a normal CPU algorithm. So this is where VMD uses GPU acceleration, and not only that, we can run it in parallel on thousands of nodes. So this is running on 128 nodes and then 2048 nodes of the supercomputer. We take what would take with one GPU node would take 2 weeks. We get that down to 19.5 minutes on 2,000 nodes. So that's about a factor of 1,000 speed up over a single GPU. And the GPU is substantially faster than the conventional algorithm. So doing that, we can basically make calculations that would have been completely impractical for you to run. Now you have a way of doing that if you have access to a supercomputer or a cluster, either at your home institution or at one of the NSF supercomputer centers. And, this isn't that much CPU time. It adds up to some node hours, but compared to what you spend on your simulation, it's nothing. That's really, when people ask us, well, I'm going to do an AMD simulation on a supercomputer, how much time should I ask for to do about my various analysis activities? Usually people use less than 10%, often even 5% or less on their analysis activities. So you can use the same machine you would use to run NAMD to do your analysis calculations. Just to give you another example of how much the technological improvements in the program impact the performance. So this is a cross-correlation calculation on that same rabbit hemorrhagic disease virus using Chimera, and I think Chimera just has a single-threaded implementation. That takes 15.8 seconds. Using the one in VMD just on the CPUs is 0.7 seconds. If you use VMD with the GPUs, it's 0.4. And now using the latest GPUs, there is a huge speed up. The newest GPUs are more than 6 times faster, about 5 times faster than the GPUs of the previous generation. So now we're at about 8/100ths of a second on the latest hardware. That's pretty awesome. So that's, we've put a lot of effort into exploiting these latest NVIDIA GPUs to accelerate some of the sort of computationally demanding features of the program. And that's what the value is for you. If you were to compare that against Chimera, so that's about 198 times faster, and that's with one node. So if you have a larger number of nodes, the speed up gets bigger. And the reason why you care about this is, if you look at the history of the simulations done by this research center, this is sort of a plot of the different key structures that this center has published its work on going back 20 years. You can see that the size of the resolved structures has increased by orders of magnitude. The latest stuff that people are working on now are in the range of 100,000 or 100 million to billions of atoms. And this isn't motivated by the availability of computational machines as much as it is being driven by the availability of experimental structures. The crystallography community and the cryo-EM community have made huge leaps in the size and spatial detail that they're able to resolve with their latest methods. And they have a need to explain the images that they're getting to better understand those structures. And that's what these supercomputers are allowing us to do. So there's a lot of pressure on us as modelers and simulators to help the experimental community improve and understand the structures that they're imaging. And they're going fast. I think one of my colleagues was just saying that they're expecting that cryo-electron tomography will be able to give us images of things the scale of the cell at a resolution around 2 angstroms. Can you imagine that? That is a huge, huge amount of structure. And so I don't know that we're going to be able to do dynamics on things of that scale, but it's very exciting, and it means that there will be a lot of projects by many people when exascale computers become available in the next few years. Things in the range of 10 to the 8th or 10 to the 9th atoms are going to become commonplace. It isn't just going to be a few people doing this. It'll be a huge opportunity for the whole field. But this presents a challenge. Those projects, aside from their computational requirements, produce a lot of data. So if you look at HIV, which is only 64 million atoms with the solvent, if you write out those trajectories, you get 1.2 terabytes per day running on a machine. This is a couple of years ago. This is 2013. Using 4,000 nodes on the Oak Ridge Titan machine, if you ran flat out for a day, you get about 1.2 terabytes or thereabouts. That's a huge amount of data. And one of these simulations doesn't run for one day. It runs for about 2 months. So you can imagine you end up with about 50, 60 terabytes of data for the simulation. And if you're doing sampling, you're not going to have one of those simulations. You'll probably run it 2 or 3 or 4 times, maybe more. And so this is becoming a bigger challenge. Historically, The I/O that we did for these simulations wasn't a big factor. In fact, MD as a community is small potatoes compared to the other things being done on these supercomputers, like weather simulations. They generate much more data than we do. But even then, we're headed to an area where, for us, it matters because it's going to impede your work. You're going to be waiting on all this stuff. And there's a couple of factors here. One is these things are getting so large, you can't really afford to copy them home. We used to, as a laboratory, run our simulations on these supercomputers and copy those trajectories back to our own lab. And we would run VMD here, and we would do all of our simulation preparation and analysis on our own machines, and that worked great. And that was fine right up until people started doing things that were on the order of 100 terabytes, and then you can't necessarily afford to own the petabytes of storage it would have that you'd need for all the people in your lab. And the other factor is it can take weeks just to copy the files. At one point, one of my colleagues, he did a protein folding simulation back in 2009, and at the time he did it was a moonshot. It was a hero simulation. He ran it for the better part of half a year on, I think it was 256 nodes, and he produced 45 terabytes. Well, one day, the Supercomputer Center said, hey, we need you to get that file off there. We need that space back. You're consuming too much of our disk space. We need you to move that. If you don't take it off, we're going to delete it for you. And we'll give you a couple of months, but that's the end of this. You gotta move this off our machine. He said, sure, no problem. He started trying to transfer this file, and after the first 30 days, and it wasn't done yet, this is the huge number of these trajectory files, he started to panic because he realized he was quickly approaching their deadline to delete his stuff, and he had been trying hard to copy it off. And, we're not talking about transferring the file from here to the moon. We're just talking about a couple of states away, but that's how difficult it is, and that was several years ago. It has gotten a little bit better, but not markedly better. So what that means is, going forward, you're going to have to mentally prepare yourself for the idea that it will no longer be practical for you to transfer your files all over the country with impunity. That's not going to work anymore. These files are getting so big, you're going to have to do an increasing fraction of the work you do on the big supercomputer. And this is unknown territory to all of us. It is a new area with a bunch of new problems. But there are opportunities too. So the first thing is, if you have to do all your work there, that means you're going to have to use things like remote visualization. You probably won't run VMD on your laptop. You may run it on the supercomputer itself. But the benefit of that is you can use a huge machine like Blue Waters, where you have 22,000 CPU nodes and 4,200 GPUs. Can you imagine the kind of movies you can render with 4,200 GPUs? I mean, it's mind-boggling. Or the analysis. You have a big storage system. So running VMD on Blue Waters on 8,000 nodes, we can read a 231 terabyte trajectory set in 15 minutes. That's pretty amazing. That's something you would never be able to do, in your natural life on a laptop. So there's an opportunity there as well. Working with these large structures, VMD has evolved better support working with very large structures that have tens and hundreds of millions of atoms. And some of the things that enable that are, for example, we have a graphical representation called QuickSurf. That's a surface representation. It's not a solvent-excluded surface. It's a Gaussian surface. But the value of it is it allows you to very easily make representations of huge complexes, and it is GPU accelerated, and on the CPU it exploits vector instructions, so it's very fast. You can actually animate the molecular surfaces interactively, which is very exciting. And it's easy to use that in concert with other representations. It can be dialed up or down in terms of how much resolution it gives in the final image. And it's very compatible with other things. Like here, we've shown a coarse resolution molecular surface of the HIV capsid, and you can see the details of ions going in and out through this pore and the hexamer. This is another one of these examples with the ambient occlusion lighting and shadowing. You can see very easily that these are all pores because they're dark. And you can see there's a pocket there or a cavity. If I rendered that with OpenGL, you wouldn't be able to tell that there's a hole unless you had it exactly lined up. It's one of those nice examples in the movie. Here's another example of an HIV movie. The chunky playback is my poor laptop. This PowerPoint presentation is about half a gigabyte, so you got to forgive it. It's a $280 laptop that I use when I travel to third world countries, and I'm worried about dropping it. It's actually hit the concrete 3 or 4 times, so it's actually pretty amazing it still works. So this is an example of a movie that was rendered using ray tracing and VMD. And then we'll zoom in on one of those hexamers right there. And you can see there's a transparent surface drawn over the exterior of the hexamer, and then you can see the bonds representation and the interior. And we can turn different surfaces on and off and change the representations. There are built-in tools in VMD for making both very simple movies that are just like a rotation movie that loops, so for like PowerPoint. And you can make more complicated movies like this using a tool in VMD called View Change Render, where you can save a series of viewpoints and tell it to make a movie sequence that sort of interpolates the view between these viewpoints. And right now that tool is somewhat primitive, but we're working on making it much better so that you can make more sophisticated movies more easily in VMD without having to learn how to use Blender and all that stuff. Of course, VMD can export scenes to files that can be loaded or displayed with Blender or Maya or other professional rendering tools. But our goal is to make it easy for you guys so you spend more of your time in VMD where you're familiar with all the settings and things and to be able to do the stuff you want. So here's another one. This is an example where we take QuickSurf over this photosynthetic patch, and we start initially with a very coarse representation, and as the camera flies in, we will make the surface more detailed. So now you can see atomic detail. We change part of the interior there to be transparent, and we put a light inside, and it sort of lights up the interior, and I'll let this loop again so you can see that. This was actually done using the CPU ray tracer called Tachyon that's built into VMD, but it was run on one of the big machines back in 2011. So something like this, this is 20 million atoms. This would have been a challenge for us back in 2011, but we were using machines that only had 6 gigabytes of memory on the nodes. So if we can do it, you can do it better. It's of course today that's no big deal. Let's see, I'll skip through some of these. Going forward, we put a lot of work into expanding VMD to support larger structures. As of the most recent version, you can load up to 2 billion atoms in a single molecule. I don't recommend trying to interactively draw it with OpenGL. This is where OpenGL has trouble, but the ray tracer has no problem at all. So this is an interesting area because it's at the crux of where ray tracing becomes more interesting as an alternative, even for regular interactive display. And so going forward, the OpenGL display window you see in VMD now, works on your typical laptop, et cetera, but we're going to be putting a lot of energy into enabling a ray tracing based renderer in that window as an alternative. And for these huge structures, it'll actually probably run faster than OpenGL does. So this is an example of a coarse grain simulation of an entire protocell with, I think it's somewhere around 113 million coarse grain particles, if I remember correctly, and several thousand proteins embedded in the membrane. And the ion, you see about 1% of the ions are shown there. If we showed them all, it looked like an opaque cake of ions. And then you can see, and this is another cute thing you can do with ray tracing. You can have mirror reflections, so you can see the reflection off the surface of this solvent here that they cut away. Some of the things we're working on going forward then are supporting interactive visualization in VR head-mounted displays. And I'm hoping maybe there's a chance to show some of these guys. Do they have a coffee break that's long enough to give them some demos?
Oh, sure.
Yeah,
we should. In the afternoon, if they want to take a break from the tutorials,
so
we have a virtual reality room in our group that you can go and actually see this live.
Yeah, I think this would be a nice bonus since they're physically here in Urbana. They should get a bonus for having traveled all the way here.
Day, so.
Yeah. So, and then another thing we're going to show, or we're working on implementing in subsequent versions of VMD is having some basic remote visualization features built into the program so that you won't necessarily have to use VNC or tools like it to do remote visualization from a supercomputer. So that'll be very exciting. And that'll let you do things like share sessions with a collaborator. Right now we do this with a great commercial tool called DCV, and I'm going to give you a little quick demo before I run out of time. And we're going to have we'll have a simple version of that built into VMD. And so this is an example. Interestingly enough, VMD was originally a cave application. So I doubt any of you have ever even heard of a cave. A cave is basically a holodeck. It's a 10 by 10 cubic room where each of the walls has a rear projection system. And as you walk around in the room, you wear special glasses that have a magnetic tracker, and the computer knows where you're standing. And as you look around, the computer is changing the scene according to what you're looking at. And these were great, but it cost about $1 million to build one of these things. And those projectors had to be stereoscopic, and I think each projector back in the 90s would have cost about $20,000. So you can imagine the bills add up very quickly. And to do this, the computers we had at the time, they had to have 6 GPUs in them, and those GPUs cost about $50,000 a piece. So pretty soon you're in the millions before you even snap your fingers. So the thing that's really cool is the fact that now these Oculus Rift and HTC Vive and the Google Cardboard are making virtual reality head-mounted displays a commodity, and the modern computers are fast enough to drive this kind of display. That's the reason we didn't use head-mounted displays back in the 90s, is computers just couldn't keep up. So we had to do it this way for reasons I won't explain. But this is a huge opportunity because it means in the next 5 years we'll be able to use this stuff in our science as a daily activity, and all of you will be able to have the equivalent of a holodeck in your office. It'll cost you no more than a typical PC, and that'll be great. The challenges we have to overcome are, how do you use while wearing a face mask essentially that excludes all of your room, how do you collaborate with the guy standing right next to you or your experimental colleague across the country? There are lots of challenges to be solved, but the cool part is we can do all the same kind of rendering in a virtual reality environment. This is a spherical projection, kind of like if you unfolded a world globe onto a planar sheet. We can do all the same kinds of rendering in VR that we would do conventionally, so that's very exciting. So you can see we can have depth of field for this ion that's very close to the camera. We can see the crisply focused RNAs out there, and so on. This is an example of a previous generation Oculus VR display and some custom lenses that I built with a 3D printer and some off-the-shelf optics. And we're working very hard with the hardware vendors to improve VMD using their latest technologies, doing things like saving your laptop battery life, doing power measurements, using fancy supercomputer rendering nodes, and using the VR displays and all kinds of different hardware. And we're working with researchers at other universities on new molecular visualization algorithms, new techniques, and all kinds of cool stuff. So hopefully we'll have lots of good stuff to show you guys. So if you have any questions, now's a good time. And I will then switch and give you a little demo of the remote visualization I was talking about. So this is, I think my network now, is it dead or alive? I think it's dead. That's why YouTube wouldn't play. Let me escape out first. So we'll try making the network come back. But why don't you guys ask any questions if you have some? Anybody have any questions?
One thing that I would like to mention was just when John was talking about big system, he said this sentence, HIV capsid, it's just 64 million atoms. I love when people from this lab say, oh, it's just 64 million atoms, it's a small system. So at least from the group that I come, that is something huge.
Yeah.
So when you come to this group, you start to get used to this kind of things. Small thing. Something below 60 million is small.
Well, it's small in terms of the challenge it presents to the software, but that's kind of good news for you because it means that things that have fewer atoms yet will run that much more easily on conventional commodity hardware. Yeah, we could try a wired network, see if it does us any good here.
And this capability of loading and simulating big systems actually is also a good development even for tools like VMD to prepare small systems that enable us to create bigger system, or let's say more close to be safe for the user system using condition and small tools.
So this is a VMD session running on a computer in our server room somewhere else. I just gave a demo of this running from Stockholm, Sweden. So not only can I do it in the same building, but I can also do it halfway around the world. So it doesn't just work if you're physically co-located. The only requirement is that you have a decent network connection. And I did it live in my presentation in Stockholm, Sweden, literally 6 days ago, using Wi-Fi in an average lecture room. They have better Wi-Fi than we do, apparently. But the cool part is, you can do all the usual things. I can open the graphical representation menu in VMD. Let's say I wanted to, I'm showing all the atoms right now in a lines representation. I can then, once I get this, this thing doesn't like to figure out, there we go. So I'm going to show the whole thing as a surface. And now I'm going to change the color. I'm going to set the color by hand to blue. And now I'm going to change the material. So you can see it looks like a big solid block. So that's the whole periodic cell of this satellite tobacco mosaic virus. I can then change it to this glass bubble. And then I'm going to change the rendering mode to high quality. So this is a little idiosyncrasy of VMD. By default, it has 2 ways of using it, or 3 ways of using OpenGL. The default way is called normal, and it's significantly lower quality, but it works even on broken graphics drivers. And so we have that be the default because you never know. You update Yosemite to Sierra, and pretty soon your Mac doesn't work anymore. And this one will still work even under adverse conditions. GLSL does a much better job drawing transparent surfaces. So now I've shown you the solvent box. And this is like I was describing before. If you look straight in the surface, it's mostly transparent. But if I zoom out, if you look at the edges, they're then opaque. And so this is a great material property. This is this glass bubble. And so you can use this anytime you want to show some detail in an interior and you don't want it to be obscured. So another thing that's interesting about VMD is that, really it works by superposition of a bunch of different graphical representations. So I just created that one. I can create another one. I just cloned it. But now I'm going to change the atom selection. I'll say protein. And so I'll see the capsid. Now I'm going to choose a more diffuse surface. And instead of coloring it by that, I'm going to color it by atom name. Now I'm going to change it from showing protein. I'm going to slice it open. I'll say protein and x greater than 0. So it's going to cut it halfway open. And you can see I just cut that guy open like this. So I have depth queuing turned on. So even with OpenGL, you can kind of see, if I rotate it around, you can see where there are cavities and pockets. And I'll show you now, this is one of these examples. I'm using a Linux machine. I'm going to go ahead and get ready to do a run of the ray tracer. I'm going to turn on shadows and ambient occlusion lighting. You see nothing happens in OpenGL when I do that. These don't affect OpenGL at all yet. I go into the render menu. And now on this machine, I have all the different renders. Now, if I have a GPU-accelerated machine with one of the NVIDIA CUDA-capable GPUs, I will see these 2 options, Tachyon L optics. And the one that says interactive GPU-accelerated, I'm going to use that one. And I'm going to go ahead and say start rendering, and a new window will pop up. And now I can render this, and you can see it has the nice shadowing effect. And I'm actually able to rotate this around. And as I let go of the mouse, it refines the image and it converges. So it's using this Monte Carlo sampling technique to improve the image as we fly around. And so this is what I was describing before. This is the key technological advance. We had ray tracing 20 years ago, but it took a minute to generate an image, and you couldn't see any intermediate result. Now, with the advent of GPU-accelerated rendering for ray tracing and the newest CPUs, we have hardware that's fast enough we can actually do this interactively, just like we would with OpenGL. And but then let's dial up the complexity a little bit more. So I'm going to add another representation. And so far I just showed surface representation. Now I'm going to show the ions. I'll draw those with van der Waals representation. So there they are. So you can see all the ions in there. And I think I'm going to go ahead and add the RNA. And I'll say nucleic. Oops, if I can spell. So there's the nucleic acids, and I'm going to draw them using the new cartoon representation, which will just draw ribbons. And I'm going to color them by residue. No, not residue. I forget what I want. There we go. By residue name. So now I can see the nucleic acid inside there, right? So you can see now in this menu, I've got on the left-hand column, various representations are shown, and you can see how they were colored by either by color ID, which is manually selected color, by the atom name, by residue name, and then you can see there at the edge the atom selection text that's used for each of those representations. Cool thing that you can do in VMD is you can toggle these on and off. So let's say you're in the middle of doing various things and you want to make a variety of figures. You want to show just the surface by itself without I want to show that virus capsid without the RNA in the interior. Even though I created that representation for the RNA, I can just hide it by double-clicking it. So you can see it turns red like that. That's very easy to do. I showed this to another group, and they were all like, "Oh, how did you do that?" Well, I just double-clicked. So in the same way, if you have a bunch of molecules loaded, VMD can actually be told to load hundreds or thousands of molecules. You can individually turn molecules in their entirety on and off by toggling D, which is drawn, and you can do a bunch of other tricks. And so now that I've got that, I could go back here, and I'm going to do one of those fancy ray tracings again, but now I have all this other stuff in the scene. And we'll start outside of the box. And I'm going to turn on depth of field 2. So we get that nice focal blur trick, and we'll go ahead and run that. All right, so now I've got the focal blur turned on. I should be able to toggle it on and off. There we go. Yeah. So good. So now I can rotate this around, and you can see while I'm rotating, you see the little shadows, those ions on the surface. As if I let go, then it has enough time to finish doing all the lighting calculations. Right now, those shadows are very dark and they look very harsh. If I let go of the mouse, they smooth out because it takes light samples from all the other directions, so you get to see that Monte Carlo sampling do its refinement. And now I can turn on the depth of field, and let's fly inside the solvent box. Now, when I'm moving, you can see those spheres look very speckly, but if I let go, they will refine and start to get progressively smoother. Now, in terms of what, like to do this, okay, obviously my little puny laptop that cost me $280, it doesn't have the hardware to do this kind of rendering that fast. But it can do a decent job with a simple scene or, maybe a structure that's not quite that large, just using the CPU. And so our goal, in developing this feature in VMD is to support both the best stuff like your GPU-accelerated NVIDIA cards, but also your typical run-of-the-mill x86 laptop. And so then while I have this view set, I can also do things like move the focal plane in and out, like I can move it to just the ion right in front of my face, and I can make everything else fuzzy in the background. I can make the depth of field stronger so that only the exact thing I want is crisply in focus. That's a very extreme example, but I could do that all throughout the scene, and I can make it so that you don't even see the thing that's right in front of you. So it's almost like having the atom selection. You can leave it there, but have it sort of diffused out so it's not distracting the viewer. So I've gone very far with this. Normally you wouldn't do anything that crazy, but I just wanted to give you an idea of the range of things you can do. And of course, you can turn these things all on and off while you're flying the camera around. So I can turn shadows on and off. So with no shadows, it looks like this, right? Looks basically like how it would look in OpenGL, except for my spheres look perfect all the time. Look at that gorgeous round sphere. And then I can turn the shadows back on and see what a difference that makes.
We are already at the time. But
Yeah, I know. So yeah. Good.
We can wrap up.
So you guys want your coffee? Yeah? All right. Please do. All right. Any last questions?
Quick question.
Yeah.
So when do you prefer to choose perspective over orthographic or vice versa?
Well, orthographic is very good at showing you, preserves spatial relationships. So if you, let's say you're looking at this virus, I'll just do an orthographic projection. The value of orthographic is, if I'm wanting to show something that I'm wanting to represent two things being the same size, despite being at a distance from each other in the scene, if I show an orthographic projection, let me just toggle this. I'll turn that off too. So the thing about orthographic is you don't get that depth impression that you had before. You see what I mean? As I rotate this around, immediately it's less clear what's in front and what's behind. And that's one of those trade-offs you're making. The value is, when I align the box like this, the front surface and the back surface are exactly aligned. They look exactly the same size. VMD has, for example, a tool in it called a ruler. There's a little extensions menu here. These are some of these scripts, by the way. You can write these. One of my friends wrote this little ruler tool. So we'll tell it to turn on the ruler, and we'll have a grid rule. Now look at that. So now we have this grid with a set grid spacing, and when I use an orthographic projection, all the distances you see drawn, whether it's in the front or the back, that's a uniform distance scale all the way from the front and the back. If I were to draw that in perspective, that distance scale is only correct in the exact plane in which it lies. Does that make sense? And so the value of orthographic, when you're trying to show something that's more like a floor plan of the molecule, you want to show a top view or a side view or the arrangement of different components from an architectural perspective, that's what orthographic is good for. But when you're showing things, especially when you're down inside the molecule, up close, that's why if I were to characterize this, I would say crystallographers like perspective views, or they often like perspective views, and sometimes they like stereoscopic views because that spatial information is very important. But when you start working with huge structures, like something like HIV or the light harvesting structures, you may want more of an architectural view because it's like the difference between looking at a model of some detailed thing like a cell phone versus looking at a city. And when you look at the city, the orthographic view is often the better choice. I don't know, maybe Joao, would you like to comment or add anything?
Most of the time, when you are trying to look at the structure as a whole, the orthographic view is better, even to see some movements of your structure, because you see, I would say, without all the artifacts of a perspective that you are being distorted, all your structure is being distorted because of the view. And even to make some, let's say, publication image, I would say orthographic is better, not only because your ions don't look like eggs as well.
Yeah.
So they
Well,
look like spheres.
The ions, when you get things, that's one thing, when you get to the corners of a perspective view, things in the corners get distorted because it's kind of like looking out of the corner of your eye. If you put your face that close to the monitor, it doesn't look distorted, but from when you're standing far back, it would be an unnatural perspective. And so that's like when you look at paintings, you want to stand at the right distance to appreciate a painting because they were intended for you to view it at a certain distance. And if you look at a distance other than that, it doesn't look right. With an orthographic view, it looks the same no matter what distance you look at it from. But with perspective, it can look very unnatural and strange if you rendered it with an extreme field of view, but then you're standing very far back. It looks very weird, or vice versa. But I was going to say also, in VMD, this display settings menu, you can change the parameters for the perspective projection by changing screen distance, screen height. This is a pretty wide field of view because the screen height is tall relative to the distance back from so it's basically has a very large vertical field of view. If you want to make it less of a strong perspective, you can change the screen height and make it smaller. Let's fix this. And by making the screen height smaller, it sort of has the effect of zooming in on the scene a little bit. But then if you look at the corners, now if I look at the corners, the ions that are in the extreme corner aren't as distorted. And if I go further, like this, it's now becoming closer and closer to an orthographic projection. Those spheres no longer have much distortion at all. They look perfectly round. So that's a very easy way. You can have as wide of a field of view or as narrow of a field of view as you want. The more telephoto the view becomes, the more perfectly circular things look and the more it approximates an orthographic projection. So an orthographic projection is the equivalent of looking at something from an infinite distance with infinite magnification. It sort of cancels out the perspective foreshortening effect.
But the only way to really understand if you are doing the right thing, choosing orthographical perspective, is to try.
Yeah.
Try, change your view, change your perspective, and say, okay, this way I show what I want to show.
But the easy thing is, if you want a wider field of view, make screen height bigger. I mean, if I make it really large, now you can see it's super distorted.
And you have eggs.
Yeah, and that's Egus Maximus, right? The max is super distorted, but this is, we would never do that. Not even the widest field of view head-mounted display can pull that off. So something, like this is getting to be, like when the height and distance are the same, that's basically a 90-degree field of view. That's like what you have with your normal eyesight at a normal viewing distance like this. So, if you make those the same, that's not the default, but if you make those two numbers the same, 2 and minus 2, magnitude-wise, are the same, then it looks like what you see with your natural eyesight. So that's a very convenient thing.
Let's take a break now.
Yep.
And let's say, what's 11?